Lissa Productions.
Welcome back to Experimental Physics. Today we begin an investigation of the temperature dependence of electrical resistance in superconductors. And just like ordinary conducting materials, the resistance of a superconductor at any given temperature can be found by measuring the voltage across the sample and the current passing through the sample, and then using Ohm's law to determine the resistance. But unlike ordinary conducting materials, the resistance of a superconductor actually completely goes away below a certain critical temperature. So the goal of this experiment is to map out the behavior of the resistance of the material as a function of the temperature and discover this critical temperature at which the resistance completely goes away. Now, how will you know when the resistance is zero? Well, you'll have a non-zero current passing through the sample, but the voltage on the sample will be zero. So from that you can infer that the resistance is actually zero. So the circuit is similar in some ways to the one we used for ordinary materials, but there's some important differences. In this particular case, we'll show you a close-up of the circuit shortly, but the superconducting sample actually has 6 electrical connections instead of just 2. So it's important to know what the function of all of these connections actually is. We use a 4-point probe to determine the resistance of the sample. So there's a pair of wires that carry the current into the sample and out of the sample, and then through the meter to measure the current. There's another pair of wires to measure the voltage on the sample, and those will go to the voltmeter. And then there's yet another pair of wires coming out which are connected to a thermocouple. So these will run to a third voltmeter to measure the voltage on the thermocouple, and that will be used to sense the temperature of the sample. So what we'll do, instead of actually calculating resistance and plotting resistance versus temperature, there's a labor-saving trick that we can do. We can measure the voltage on the sample, which is related to the resistance from V equals IR. So just plot the sample voltage as a function of the thermocouple voltage, which is related to the temperature. Now, when the material is in the liquid nitrogen, the material will be below its superconducting transition temperature, so the resistance will be completely zero, and the voltage on the thermocouple will be about 6.4 millivolts. So that's one data point on your plot, 6.4 millivolts when the sample is completely in the liquid nitrogen. But then what you'll do is to raise the sample up out of the liquid nitrogen. So let me sketch on here the container with the liquid nitrogen in it. So we'll put the sample in a container with liquid nitrogen. So the liquid nitrogen will be in an insulated container, and we'll put a piece of foam insulation on the top just to keep the thing cold. So this is the foam insulation. And the sample, instead of being completely in the liquid nitrogen for the whole time, you'll raise it up so that it's no longer in contact with the liquid nitrogen, but it's still underneath this insulating layer, so it's now in a cold vapor environment, and that's what will allow for the variation of the temperature. So as the sample gradually warms up, it starts out at zero resistance in the liquid nitrogen, and then gradually warms up to the point where it ceases to be a superconductor, and the resistance reappears, and then it goes back to ordinary conducting. What you'll measure with your voltmeters is, again, 6.4 millivolts on the thermocouple voltmeter when the material is in the liquid nitrogen, and then when you raise it up out of the liquid nitrogen, it will gradually increase in temperature, and the voltage on the thermocouple will slowly decrease until you hit the critical temperature. Then the resistance on the sample begins to reappear, so the sample voltmeter will start to read something that's non-zero, and that will increase as the material warms up, and then it will gradually go back into ordinary conducting. So we'll use the thermocouple voltmeter to sense the temperature and the sample voltmeter to infer the resistance. So the plot that you get in the end will look sort of like this, with lots of data points when the material is in the liquid nitrogen, so the resistance of the sample will be 0 for a small range, and then it will become non-zero. So the goal is to get lots of good data in order to sense the transition temperature, the critical temperature for becoming a superconductor. So now let's take a close-up look at the electrical circuit and the contact connections that you'll need to make. Okay, so connecting the superconducting sample, we have specially prepared samples. This gray material is the superconducting ceramic, and there are 6 electrical connections coming out of this thing. So the first thing that we want to do is to connect the series circuit for carrying the current. And you'll need one of these banana plug leads coming from the power supply and into the ballast resistor. So in this case, the ballast resistor simply serves to limit the current so that we don't fry the 4-point probe inside the superconductor. So from the power supply into the ballast, and then take one of the black wires. We'll plug this into the ballast, so from the power supply into the ballast, and then into the sample. Then out of the sample into a meter for measuring the current. So we'll plug this into the 20 amp input. And that will measure the current, and then out of the common connection on the current meter and back to the power supply. So that's the complete circuit for carrying the current from the power supply into the ballast, out of the ballast into the sample, and out of the sample into the current meter, and out of the current meter back to the power supply. Then for measuring the voltage on the sample, there is a pair of leads connected to a double banana plug, and you simply plug both of these connections into the common connection and the voltage connection on the voltmeter, just like this. And we'll set this to the 200 millivolt scale. It's important to have this set to get the extra precision. So 200 millivolt scale for the sample voltage. And finally, the other 2 connections on this sample are for the thermocouple. And these are a special purpose pair of connectors which are designed to receive the standard pointy probes from a multimeter. So just plug one of the pointy probes into that socket and the other pointy probe into that one, and sets the thermocouple voltage also on the 200 millivolt scale. So both the sample voltage and the thermocouple voltage are set on the 200 millivolt scale. Then what we'll do is to take the entire sample and slip it through the slot in the cover for the insulating cup, and take a piece of foam insulation and put that over the top of the sample. And when there is liquid nitrogen in the cup, you simply dunk the sample directly into the liquid nitrogen. You should get 6.4 millivolts on the thermocouple and 0 voltage on the sample voltage when the material is in the liquid nitrogen and superconducting. But most of the data will be taken by lifting the sample out of the liquid nitrogen. So we'll just clamp the sample onto this stand. And raise it up out of the liquid nitrogen, but still underneath the insulating layer of the cup. That will keep it in a cold vapor environment, but above 77 Kelvin, so the sample will slowly increase in temperature. And what you should see is that the thermocouple voltage will slowly decrease from 6.4 millivolts on down, and the sample voltage, when you reach the critical temperature, will begin to reappear. So you want to take lots of good data, sample voltage as a function of thermocouple voltage, to find the critical temperature. So to recap the goals of the experiment, you want to gather enough good data in order to determine accurately what the critical temperature is for this material to become a superconductor. To do that, you measure the voltage on the sample as a function of the voltage on the thermocouple, beginning with the sample completely in the liquid nitrogen, and at that point the thermocouple voltage should be about 6.4 millivolts. Then you raise the sample up out of the liquid nitrogen, so it's no longer physically in contact with the liquid nitrogen but slightly above in a cold vapor environment. That allows the material to gradually warm up, and you'll see the thermocouple voltage slowly decreasing from 6.4 millivolts down to the point where the material ceases to be a superconductor. So it will rapidly transition back to ordinary conducting, and the trick will be to gather enough good data in this rapid transition region so that you can determine where the critical temperature occurs.